Okay, I think we can start now. So last topic which I started was security of DES. So today I intend to finish security in DES and then start a new encryption method. So let us quickly finish this. This is comparatively very simple for you to understand. Right. So security in DES can be broken by three methods. In fact, there are three types of attempts. One is brute force, but if we apply brute force, then it requires 2 raised to 56 keys to be tried, right? Suppose if we consider that complement is possible and only half of the keys we have to test, then 2 raised to 56 divided by 2, that means 2 raised to 55, 56 minus 1. So only 2 raised to 55 keys are required to be tested. But this 2 raised to 55 is also a huge number, right? So that is very difficult. It is very complicated to test 2 raised to 55 numbers. It's a huge number, right? So half doesn't make any much difference in the number, the value of the total numbers. Differential cryptanalysis is a different topic we will discuss later. Linear cryptanalysis is relatively newer. Now, there are the variation, the DES, one DES structure was discussed earlier and that we follow. So in this diagram, when you are seeing DES, that is one structure. Okay. So 2DES is applying DES 2 times before we get ciphertext and with 2 different keys. So you can see that it is a plain text which goes through DES with cipher key of K1 of 56 bit. Naturally, it will create 16 rounds. So 16 48-bit keys, but from this 56-bit key. Then it goes through another DES block with another cipher key. Again, it is of 56-bit. So again, it has 16 rounds, which has 16 different keys of 48 bits. So this process is followed 2 times. So cipher key length is 56 plus 56. Okay, and that is 112 bits. So if we apply encryption with a key of 112 bits, brute force is not possible. Okay, so 2DES is also called as 2 times DES or composition of DES. Okay, or DES into DES. So DES block has its equivalent DES inverse block that is performing decryption. Okay, so this 2DES cipher can be attacked by a method called meet in the middle attack. Okay, meet in the middle. So what happens in meet in the middle attack? So you see first the encryption process and decryption process. Encryption is plain text, goes through DES. It generates intermediate output X. This is actually a ciphertext, but this ciphertext is again goes through DES block again, and then it produces ciphertext. So this becomes our final ciphertext. Okay, so there are 2 keys, K1 and K2. Now decryption, see decryption, DES inverse. Okay, so this ciphertext goes through DES inverse, that is decryption block, with key K2. Okay, and then it produces some intermediate output, that is X. Okay, and that is again plain text, but this is not the actual plain text because we have to go through 2 rounds of decryption. So again, DES inverse goes through and it produces P, right? With K key 1. So you can see that this X remains same in middle part, right? So what is X? X is DES K1 of P. Okay, and X is also DES inverse C K2 of C, right? So here ciphertext is DES K2X and plain text is DES inverse K1X. So you can see that this DES P K1, okay, this one left side is equivalent to DES inverse ciphertext K2, right? That means if you encrypt plain text with key K1, it is equivalent to you decrypt ciphertext with key K2, right? So that is meet in the middle, right? So this, if we find this, then we can find K1 and K2 pair, and then it can be broken, right? So if we find this entry, so to perform this meet in the middle attack, we need to perform chosen plain text attack. Am I audible? Please respond. Am I audible? Okay. Okay. So this is chosen plain text attack, and we assume that F has L pairs available. So PI-CI pair is available for I equal to 1 to L. So we have to create two tables, table 1 and table 2. In table 1, we have P1, P2 up to PL, right? We have plain text and we have corresponding ciphertext. So P1, I equal to 1 to L, P1, P2, PL, and for that we apply key K1, and then we generate all possible key values 0 to 2 raised to 56 minus 1, because key length is 56 bit. So all possible keys of value 0 to 2 raised to 56 minus 1 all are tested and encryption is done, right? So with K1 equal to 0, if we apply DES P1, then we get this entry, right? So this is encrypted text. This is encrypted text with K1 equal to 0. This is a encrypted text with K1 equal to 0. And this way we prepare this table, okay? Now second table which we prepare is C1 to CL. Now again this, we have this pair, so L pairs are there, L entries of ciphertext are there, and we take keys from 0 to 256 minus 1, and then we apply this table. So we have two tables, okay, and then we match because we know that DES of P with K1 key is equivalent to DES inverse of C with K2 key. So if we find these two entries in this two table, if we match two tables and entries, then we need to search row I of table 1 and row J of table 2 such that all values agree, right? So row I of table 1 is same as row J of table 2. So thus we need to search for row I of table 1 and row J of table 2 such that these two are equal, right? I and J should be equal. Two entries should be same. Okay, I and J value are different, but the value stored at ith row and value stored at jth row should be matching, right? But this process is time consuming. And what are the reasons for that? So the first reason is that to create table 1 and table 2, we need to do DES and DES inverse many times. How many times? We have 2 raised to 56 keys and L plain text. So 2 raised to 56 into L encryptions we have to do. Similarly for table 2, 2 raised to 56 into L decryptions we have to do. So total number of encryption or decryption is equal to 2 raised to 56 into L plus 2 raised to 56 into L. So this is equal to 2 into 2 times 2 raised to 56 into L, and that is 56 plus 1. So 2 raised to 57 into L. Okay. Now this is number. Okay. This is the number of operations we need to do, and how much space is required. So the space requirement, we need to create a block of 64 bit. So 2 raised to 56 into L into 64 plus 2 raised to 56 into L into 64. This is equal to 2 raised to 57 plus 2 raised to 64 means uh, 2, 4, 8, 16, 32 and 64. 2 raised to 6 plus 2 raised to 6. So 2 raised to 62, right? So if encryption and decryption takes t units of time, then we need 2 raised to 57 into L into t unit. Okay. So this is the time requirement. So this is the huge amount of time. Second reason that it is a time consuming is that to search row I from table 1 and row J from table 2, such that row I of table 1 equal to row J of table 2, the values at corresponding two rows are same. We need to do many comparisons, right? Sorting operation, comparison. Not sorting operation, but comparison operation. Row 1 needs to be compared with all rows of table 2. If no match is found, then row 2 of table 1 needs to be compared with rows of table 2. And therefore, this is time consuming. So if it is in the first or second rows, then it is fine. But as we have to generalize, if suppose it comes after 2 raised to 50 comparisons, then it's a huge number, right? So provided that you have L pairs, sufficient memory and processing power, you can launch meet in the middle attack to guess the keys K1 and K2. Now, if you want to have such a huge memory and processing power, you need to take high performance computers. Okay, high performance computers are, it is a separate branch. High performance computing is a separate branch of computer science. Okay, and usually in scientific applications and these network security attacks, these high performance computers are used. So K1 will be I and K2 will be J, where I and J are value from 0 to 256 minus 1. Like 2DES, there is another concept called 3DES. Okay, in 2DES, it was, now there are two variations. In 2DES, DES was applied 2 times. Here it is applied 3 times with 3 keys. Okay, so a plain text goes through DES with K1 key, DES with K2 key, and DES with K3 key. And finally, what it produced, that is a ciphertext. So what is happening is that it is using 56 into 3, 160 bit key cipher key. Okay, that is used. Now there is a variation into this. Second type of 3DES using 2 keys is that first plain text goes through DES with K1 key, then it goes through DES inverse with K2 key, and then it goes through DES again with K1 key, right? So this is variation, and so the decryption is inverse of that. So encrypted ciphertext goes through DES inverse with K1, DES with K2, and DES inverse with K1. Okay, and so this is now here it is important to observe that if K1 is equals to K2, if the two keys are same, then this will nullify the effect of DES and DES inverse. Okay, so first two sequence of DES function is nullified, and so it is as good as one time DES. Okay, so this is what you have to understand. So this finishes our discussion of this DES topic. Let me see this chapter slide. If just a minute. Okay. So you can refer to the book for pseudocode for DES. Okay. Okay, I will share these slides with you. Now I will start the next topic, uh, that is AES. Okay, can you see the slide? Okay, okay. So now we are going to discuss Advanced Encryption Standard, AES. Okay. So, like I discussed in the case of DES, that it was decided to be to make it as a standard by National Institute of Standard and Technology, by that is the institution in United States. So, similar to that, this AES is also designed by NIST, National Institute of Standard and Technology, that is in United States of America. Okay, so you can go through the history of AES, and it was actually launched in 2001. So it is relatively newer. So only 22 years have passed, only 22 years, okay? But it is still very useful. And because of its strength, it is used. Okay, it is again a symmetric block cipher which encrypts with 128 bits block. Okay, what is the block size of DES? Correct. Block size is 64 bits in DES. In AES, it is 128 bits, which means it is doubling the block size, right? Then DES. So simultaneously, you can encrypt 128 bits. This is the advantage, main advantage. Second advantage is that it is a non-fistal type. Okay. What is fistal type? What is fistal type? DES is fistal or non-fistal, and what is fistal type? Can anyone say? Fistal structure. It was discussed in the last lecture of second sessional. Fistal structure. Invertible, non-invertible elements. Can you recollect? Okay. It is a non-fistal type, as please go through that discussion. A non-fistal type, as the basic elements of AES are all invertible. If there is non-invertible element, then it is called as fistal. But if all are invertible, then it is called as non-fistal. Okay. So AES comes with three versions, or version 1, 2, and 3. Each one uses three different size of key. Okay. However, block size is 128 bits. The key size is 128 bits, 192 bits, and 256 bits. And in DS, you have only one structure with 16 rounds. Here, there are three variations, three different standards, each one with different number of rounds. 128 bits AES 128 has 10 rounds. AES 192 has 12 rounds, and AES 256 has 14 rounds. So this 128, 192, and 256 are actually key sizes which is used in this standard. Okay, in each of this version. Okay, and the round keys are always of 128 bits. What is a round key? Round key is this, and this is cipher key. Okay, round key is 128 bits. What is the round key size in DES? Can anybody tell? Okay. 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 So here it is 128 bits. Okay, so there are 10 rounds of 128 bit round keys, and 12 rounds and 14 rounds. So from 192, it will generate 128 bit keys. 256, it will generate 128 bits round key. General design of AES, you can see that one element in this AES is key expansion block. Okay, so there is a 128 bits plain text. So block of 128 bit is given as an input, and key expansions has input of cipher key. Now, as per three versions, 128, 192, and 256, that is given over here. Key expansion is used, and it generates number of round keys. Okay, how many keys? If the number of rounds are 10, then 0 to 9. Sorry, 0 to 10. Here, from R1 to from N1 to NR, that is number of rounds, plus there is one pre-round. Okay, so total bits which are used is NR plus 1 into 128. NR plus 1. Because there is one pre-round. Okay, so the number of round 10, 12 or 14 plus 1, because there is K0 that is applied for pre-round. Okay, and then when it goes through these all rounds, then it generates a ciphertext. Now there is a concept of byte substitution. So in that context, I will give you a brief discussion about byte, and we will move to one important mathematical discussion after briefly discussing the initial phase of AES. So byte, as you know, 8 bits, right? Byte is of 8 bits. So B0, B1, B2 up to B7, that is a byte. Word is of 4 bytes. So this is 1 byte. 4 such bytes are creating one word. So the total number of bits are 32 bits. And then a block of 16 bytes. So 16 into 8, that is 128 bits. So a block is of 128 bits, right? So to represent these 128 bits, it is represented by a block of 16 bytes. So each entry is of 1 byte. So total 16 byte makes it 128 bits. Is that clear? Is that clear? Understood? Yes, please respond. This is a very fundamental thing. You must have studied in design of digital circuit DDC course. Yes, are you there? Please respond. Please let me know. Are you listening? Have you understood any doubt in this particular discussion? It is very straightforward and simple. Okay, right. So this block of 128 bit can be represented in the byte form in a one row by B0, B1, B2 up to B15, right? So B0 to B15 is 16. 16 bytes, each byte 8 bits, 16 into 8, 128 bits. Clear? Please type. Do you remember the group concept? Group. In elliptical curve cryptography, you have studied the group concept, abelian group, then abelian group. Do you remember that? You have already done the practical of electrical curve cryptography, right? Okay, so this is also a group of 16 bytes, that is 128 bits. So here BI is ith bit, and you can see that block can be represented by 16 bytes: B0, B1, B2, B3, B4, B5, B6, B7, 8, 9, 10, 11, 12, 13, 14, 15. So this can be represented as a matrix of 4 cross 4. And to represent this block as a state, okay, so now there is another methodology to represent this byte as a state. So we can rewrite this block as state by writing S00. That means 0th row, 0th column. First row, 0th column. Second row, 0th column. Third row, 0th column. Now each one is each one is byte. So 8 bits. We have 16 such bytes, right? So byte of row 0, row column 0, row 0, uh, row 0, column 1, row 0, column 2, row 0, column 3, column 1, row 0, column 2, row 0, column 3, row 0. Okay. So state is the same 4 cross 4 matrix, and each Sij is byte. So S00 state is actually 1 byte. Okay, is this concept clear? How to represent it as a matrix? How to represent a block as a matrix? Clear? Okay. Okay. So now let us see our plain text is AES uses a matrix. Okay, AES uses a matrix. So what we are doing is that we have to create a block of 128 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 characters. Remember, each character is 1 byte. Okay, so 14 bytes of data is there. 2 more ZV append. Okay, padding Zs, so that it becomes 16 byte. 16 character is 16 byte. Now we want to encrypt it. So to encrypt it, first we represent this character as a 2-number hex value, 2-digit hex value. 2-digit means if it is 0, we have to write 00. If it is E, we have to write 0E. Okay, and remember it is a hex value. Okay, so we obtain the hex values of each of these character and then rewrite it in the form of a matrix. So A00, E04, S12, U14. Okay, so this way we arrange it in 4 cross 4 matrix. AES uses a matrix ZZ. So how do we get this hex value? So this 12 value for S, the value which we have taken is 12. So this 12 hex is then converted into binary. So if we convert this 12 into binary, then this is 1, 0, 0, 0, 1, 4 bit, and this is 2. This is again another 2 bit. So each digit is represented by 4-bit number. So we have 2 such 4-bit numbers, which makes our hex value. Right. So the total number of bits are 8. Okay. Now, am I audible now? Am I audible? Yes, I got disconnected from my laptop. So I'm just trying to log in. So please be patient. I'm just logging in. There is some network issue. Okay, now join back. Let me share this notes. Okay, now can you see the slide? Can you hear my voice? Okay. So let me discuss the structure of each round. Remember, there are two rounds, 10 rounds in uh, one AES 128. Okay, so the structure of a round is that we first give block. What is this block size? 1, 2, 3, 4, 4 cross 4 matrix. So 4 cross 4 means 128 bits given as the input. And the first stage is sub byte. Sub byte means substitution byte. So this byte which we are giving as an input, that is substituted, right? Remember initial permutation and final permutation or substitution in DES, right? So we had a table in initial substitution, and in final substitution we had a table, predetermined table, and it follows that table. Here also we have similar such table. Let me show you. Okay, this is sub-byte transformation table. You can see this is a predetermined table, and we can do sub-byte transformation. Okay, similarly we can do. So this is actually 0, 1 to 6 up to F, 0 to F, that is 16. Okay, and this is 0 to F, 16, 16 cross 16. Okay, then there is inverse sub byte table like this. Okay, we will come back to this later on. So for the moment, this is a table generated substitution, and then it goes through two operations. One is shift row. So because it is 128 byte, sorry, 128 bit, it goes through sub byte. So it again produces a block of 128 bit. So the number of bits remains same. Then it goes through shift rows. So it performs shift operation on rows. Then it performs mix column operation on columns, and then it performs add round key. So there is a round key which is added in this fourth stage, that goes through and it generates a block. That is the first, that is the structure of the round. Okay, so this one add round key is applied, okay, before first round, that is in pre-round. If you can recollect this one, there is a pre-round and there is key K0. So this one is added before round 1. Okay, round. So the round structure which we are discussing, that is before that there is a pre-round. Okay, and that uses key K0. And third transform is missing in last round. Third transform is missing in last round. Now each of this stage we will discuss in detail. What is sub byte? Okay, substitution. Sub means substitution. Okay, so what are the steps? So you can see that this is a 4x4 block and each value is hex. So this is the text. AES uses a matrix ZZ. This is our text. This is our matrix representation. So what we do after sub byte, we get 00 means if you look at this table, what is the value of 0, row 0, column 0? What is the value at row 0, column 0? $63, right? So what is happening is that we substitute, instead of 00, we substitute 63rd byte, right? Bit. Then it goes through 04. So what is the value of 04 means row 0, column 4. So what is the value in this table, row 0, column 4? F2, right? So here see F2. That is F2. Okay. 1, 2, row 1, column 2. Look at the table. Row 1, column 2. What is the value? Okay. So see, we represent here C9. Okay. So this way we prepare this substitution table. Now, if you look at this table, it is substitution table, but there is a corresponding inverse substitution table also. Now see, this table is given in the book. In inverse substitution table, the first element is 63. That means row 6, column 63. But you have to see the inverse substitution table. Row 6, table column 3. So what is the value? Zero zero. And see, what was the value at 00? 63. So when there is a 63, we have 00. Similarly, if you look at this value, F2, what is the value of F2? F and 2, what is the value? Zero 4, and it was 0. 4 is F2. Can you see? So it is invert. It is so, and this table is also mathematically prepared. It is not a random table, but it is fixed table which follows some mathematics. So first step is substitution byte. For each byte of state, let's say SRC, R means row, C means column. So so byte is in matrix and RC means row 0, column 0. First we find multiplicative inverse with respect to GF 2 raised to 8. Okay, what is GF? Can anyone say? Anybody knows GF? Have you studied it earlier? Anybody? This is a Gauss field 2 raised to 8. Okay, and that there is, it uses a polynomial x raised to 8 plus x raised to 4 plus x cube plus x plus 1. Okay, so for each byte of state, first we find multiplicative inverse with respect to Galileo's field 2 raised to 8, then pre-multiply SRC inverse. Okay, so we find multiplicative inverse, we pre-multiply SRC inverse by x, and then we XOR with previous answer the D or 63H. So y equal to x into SRC inverse XOR D. Okay, and finally we have y equal to x SRC inverse XOR D. So sub byte is a non-linear transformation. Remember, non-linear transformation. Sub byte is non-linear transformation. Okay. Now, before I begin here from this point, remember page number 4. From this point, before proceeding, I will now talk about this GF 2 raised to 8 and what this polynomial is. Okay. So remember that we are discussing AES, but first I will discuss you the another concept that is called as finite field. Okay, now for we will start some fundamental discussion of mathematics, that is finite field. So what is a field? So before I begin the definition, you just go through this diagram and you will understand the briefly about it. What is a field? See, this is group. You have studied group, right? Yes or no? Group, abelian group, right? Abelian group. Group has 4 properties. Abelian group has 5 properties, including commutative, and extension of that is ring. Okay, so ring is having closure, associative, distributive, and commutative of multiplication and multiplicative identity. Okay, then ring commutative ring and integral domain, and then comes field. So this is the scope of field. Okay, what this field is. This is a general diagram for you to create an understanding about how this field is related with some group, abelian group or ring concept which you have already studied. So I'm now discussing the formal definition of field. It is denoted by F equal to set. So it is a set. We have to take a set, like in group and abelian group we used to take set, and there was only one operator, but here there are 2 operators. So a set with 2 operators, operator with dot, operator as a square. So these 2 operators, some 2 operators we are not yet defining the operator itself, whether it is plus, minus, etc. But it is some 2 operators are taken. Okay, so we have taken some set, we have taken one operator and second operator. Is a commutative ring. Field is denoted by F, which is a commutative ring in which the second operation, this square, satisfies all 5 properties defined for the first operation. So dot operator, for first operator you have to define all 5 properties, but for square second operator you can define all but 4, all but 1, that is in inverse you have one relaxation. Okay, so that satisfy all 5 properties defined for the first operation. For first operation you define these 5 operations, properties: closure, associative, identity, inverse, and commutative. But for second operation square, we have closure, associative, and identity. But the first operator's inverse, if it is not found, it will be okay. No, not required. Okay, the identity of the first operation has no inverse with respect to second operation. So inverse has a relaxation for second operator with respect to first operator, right? So except that the identity of the first operation has no inverse. Now this second operator is distributive over first operator. Distributive means a second operator square in the bracket b into c, b first operator c, not into b first operator c. Then it can be written as a second operator c, a second operator b, first operator a second operator c. Okay, it is a distributive property. Okay, so first operator has 5 properties: closure, associative, identity, inverse, and community. And second operator has closure, associative, identity, and commutative, right? But fourth condition is relaxed. Inverse with respect to first is not required. Okay, so this is the definition of field. I hope it is clear to you. Is it clear? And I think you already remember all these properties: closure, associative, identity. Identity means what? If you multiply and its inverse, then you get identity element, right? X multiplied by X inverse is equals to 1. Okay. So after explaining you the definition of field, now I will discuss with you finite field. The definition of finite field. Finite field is a field with finite number of elements. Okay. So finite fields are very important structure in cryptography, and Galileo's showed that for a field to be finite, the number of elements should be p raised to n, where p is prime and n is positive integer. Okay, Galileo's was the one who showed that uh, if we want finite field, then we should have the number of elements should be p raised to n, and that p is a prime and n is some positive number. Okay, so the finite fields are usually called Galileo's field and denoted as GF p raised to n. Okay, so if we write 2 raised to n, whether it is p raised to n or not, yes or no? If we write 2 raised to n, can we say that it is equivalent to 2 raised to n? Yes or no? What is the value of p here? If we compare 2 raised to n, 2, yes, yes. So p is a prime number. So now, so we have understood that GF p raised to n is a finite field with p raised to n elements. Okay, now this Galileo's field. Galileo's provided the definition of finite field, and it says that the field to be finite, you require p raised to n, where p is a prime number. So let us understand what this is. So this GFP field, this field can be set. Okay, it is as per the definition of set, definition of field. What is field? It is a set with two operators. Okay, so GF field is set. Which set? ZP. ZP means 0 to P minus 1. With two arithmetic operations, addition and multiplication. Okay, so if we write GF2 where P is a prime, okay, so 2 is a prime number, and if we write GF2, then we have set of two elements 0 1. Okay, if we write P, then we have P elements. So if we write 2, then we write two elements 0 1. Okay, and we define two operators. This is our definition. Okay, this is our definition, and we have to see whether it satisfies the GF field criteria. So plus 2 means binary plus and multiplied by 2. That means modulo 2. Okay, or binary. This performs binary multiplication and this performs binary addition. So if you look at this definition of plus, this, if we add two numbers 0 plus 0, remember this is with respect to plus. Plus here is XOR and multiplied here is AND operation. Okay, Boolean algebra, you remember XOR and AND operation, the same concept is here. So when we write plus over here, it is actually XOR, and when we multiply over here, it is actually AND. Now let us see 0 plus 0. So 0 XOR 0, that is 0. 0 XOR 1, that is 1. 1 XOR 0, that is 1. And 1 XOR 1, that is 0. Similarly, 0 multiplied by 0 is 0. 0 multiplied by 1 is 0. 1 multiplied by 0 is 0. And 1 multiplied by 1 is 1. Okay. So this is the definition of GF2. Now GF5. GF5 means 0 to 4. 0, 1, 2, 3, 4. And plus 5 plus 5 and star 5. So let us see. This 5 means mod 5 we have to take. Okay, mod 5. This is modulus, remember. So here we take plus operator for modulus 5 value. So the elements are 0 to 4 and elements are 0 to 4. So 0 plus or 0 XOR 0, what is the value? 0. 0 XOR 1, what is the value? 1. 0 XOR 2, value 0. 2. 0 XOR 3, value 3. 0 XOR 4, value 4. Similarly, 0 plus 0, 1 plus 0, 2 plus 0, 3 plus 0, 4 plus 0, that is 0. Now we take second column, 0 XOR 1. So 0 XOR 1, 1. Then 0 XOR 2 is 2, 0 XOR 3 is 3, 0 XOR 4 is 4. Now 1 XOR 0 is 1, 2 XOR 0 is 2, 3 XOR 0 is 3, 4 XOR 0 is 4. Then comes 2, 2 XOR 0, 2 XOR 1, 3, 2 XOR 2, that is 4, 2 XOR 4 is 6, and 2 XOR 3 is 5, and 5 mod 5 is 0. Okay, in these values, the mod 5 is taken. So if you look at these values, it is actually a shift left. So in 0, shift left 0. In 1, shift left 1. So that is from left hand side. Into shift left 2 bits to left, that means this 4, that means shift 4 bits to left, so we get 401023. So you can see the in row it is 0 to 4, this 0 to 4, it is 0 to 4, 0 to 4, 0 to 4. Each value is modulus 5 values. Okay, so for example 3 plus 4, 7, 7 mod 5 is 2. Understood how this 2 value has come? Right, so similarly multiplication. Okay, multiplication, 0 multiplied by 0, 0, 0 multiplied by 1, 0, 0 multiplied by 2, 3, 4, 0. Similarly, this column is also going to be 0. Now, if you take 1, so multiplied by the corresponding number remains 1. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, now we take 2. So 2 into 1 is 2. 2 into 2 is 4. 4 mod 5 is 4. 2 into 2 into 3 is 6. 6 mod 5, 1. Okay, 2 into 4, 8. 8 mod 5, 3. Similarly, 4 mod 1, 4 mod 5, 4 multiplied by 1, that is 4. 4 mod 5, 4. 4 into 2, 8. 8 mod 5, that is 3. Okay, 4 into 3, 12. 12 mod 5 is 2. 5 into 2, 10. Remainder is 2, so it is 2. Clear? So here we have additive inverse. We have 0 is an additive inverse. Right? So 0, any number we add 0, we get 0. Right? And we have multiplicative inverse. So for 0, if you look at this, we don't get multiplicative inverse. But for 1, we have multiplicative inverse 1. 2, we have multiplicative inverse 3. 3 multiplicative inverse 2. And 4 multiplicative inverse 4. But it is allowed not to have 0th multiplicative inverse as per the definition that first operator's inverse is not, if it is not available, then it is fine. Okay, so the multiplicative inverse is plus multiplicative inverse plus operator for 0 is not available. Additive inverse operator is not available in the second field, second operator. So that satisfies. Okay, so we will have a further discussion on this Galileo's field in next class. So in next class, I will try to finish this Galileo's field discussion, and then we will have a discussion further on this AES. Because for AES, Galileo's field discussion is required. So I am currently discussing Galileo's field, that is from chapter number 4 of textbook. Okay, so I stop here.